Welcome back. Now we will see the estimator bias. So we all know now like what is the estimator, what is the estimate, population movement, sample movements and everything. So everything, this particular part should be clear for you. Here we are going to see the estimator bias. We are trying to quantify estimator's bias in this section. So how to quantify for the mean estimate and the standard deviation estimate or the variance estimate. This is the primary discussion. This is what you are supposed to understand and remember the formula. And I personally think like if you get any numerical side question on this area, so this should be the bias calculation. This is very easy calculation. You have to just understand few concepts and you can easily apply the formula. So let's first start with the formula of this bias, that is how to quantify the estimator bias. So value of bias of estimator is equal to, see this is how I'm reading, so you should in your mind you should read like this only. So bias of estimate is equal to expected value of estimate minus population value. Okay, so here this is a general formula. You can use it for the mean and we will replace the term with the mu. You can use it for the variance, we will replace the term with the sigma square, like this. So say if you have to write the same thing, same equation for your mean, then formula goes like bias of mean estimate is equal to expected value of estimate minus population value of mean, like this. But you don't have to think on this particular formula for specifically for the mean, because we already know the mean is unbiased estimate. So what will happen here? Because we already know this is the unbiased estimate, so value will be 0. Simple. Okay, so in this equation you already know what is the mu, that is simple mean for the population. You already know what is the bias. Only question is what is expected value of mean estimate and how it is calculated. So for this I will take just rough example, okay, instead of doing all the calculations, because it is not practically possible to calculate mean estimate in running class. So you have to draw the samples, take the value, calculate the mean. It is a lengthy process, but here I am taking a same example, old example, 100 students mock test score or FRM exam score, students exam score, okay, and we are creating a sample of 20 students or scores. So we have 20 scores and 100 student scores total. So what we will do, this is your complete sample. So first we will select 20 students. We will calculate the mean score, the average of their scores, and we will say this is A sample set and mean A. Then we will repeat the process, 20 B mu B. Again we will select third sample set C, we will call it as mu C. Now what is the condition of selecting the sample set? So first you will collect the scores and you have to put back all the scores. So your population size will always be 100. Okay, so you will select random scores. Now you got 100. Now you got 20 samples, calculate the average, put back those scores and again randomly select it. So in your imagination, how you should imagine, say you have bucket and in that bucket you have sheet of student score and you have to select the 20 scores, calculate it, again put back, again select 20, put back. But here the condition is that it should result in unique sample sets. Okay, so your A, B, C, D should be unique and there should be equal possibility of selecting all samples, all observations in your sample, like this. Okay, this is the primary condition. So here we are creating our sample set. So your sample set goes like this is your set. So say A, B, C, D and so on. Now we will have the mean score. Okay, so mean score is like you took the 20 values, calculate the average and whatever is that value for the 20 scores you selected from that bucket, we will call it as a mean score. So say in first instance you got 78, in second instance you got say 65, in third instance you got say 62 out of 100, obviously because it's FRM exam, and then out of it should be, let's take 37 and so on. So you will get all these values, and when you get these values, we will calculate the average of these values. Okay, so this average is calculated using this formula, that is your summation of all your values divided by n, and this is your expected value of mean estimate. Why estimate? Because you are creating estimate here, you are using the distribution, the sampling distribution, and based on this you are trying to estimate the population value. See here, no sample represents direct population's mean, but because you are creating a sampling distribution and calculating the mean of every sample set, and based on that you are calculating the value, so it becomes an estimate. Okay, you got the estimate here, expected value of the estimate. So if you want, you can take the example of say 10 students, write down this course, create unique samples. It is very lengthy process. Create unique samples, calculate the average, and you will get the result. This result is expected value. That's why we call it as an expected value of the mean estimate. So this is your expected value of the mean estimate. Okay, now formula for the bias is equal to bias of mean estimate is equal to expected value of mean estimate minus actual mean of the population. So how you get this mean of the population? You will directly select, wait a second, you will directly select this particular population of 100, and you will directly calculate the mean. Simple. Okay, so you got the mean here. You remember the first principle we learned for this particular part, that is for the calculation of the bias. So we call the mean as an unbiased estimator because the estimated mean, the expected value of the estimated mean is equal to population mean, right? So we already know that this value is equal to this value. So that's why result is 0. So you have to always remember this bias of mean estimate is equal to 0, because again we know that expected value of the mean estimate should be equal to this population value, and if you perform this particular analysis you will find it. Okay, so you will get the value as same as this. Okay, so expected value of the estimate will be equal to, so you have to perform the calculation, or you can directly run it in the software, then software will give you the result. And again, that's why you have to always remember the sample mean is unbiased estimate. I'm repeating it again and again because highly testable. Sampling mean is unbiased estimate. Next is for the variance bias, and we already know variance is biased. Okay, so again we will use the expected value here, right? Expected value of the variance estimate, and we have the defined rule for calculation of the expected value of the variance estimate, and this is your n minus 1 divided by n into sigma square. So you have this population variance, and if you multiply n minus 1 divided by n, if you perform this calculation, you will get your variance of, just a second, let me rephrase the statement, you will get the variance, estimated variance of your sample set. Okay, now again try to recall, we said that your sigma square estimate formula is, and which is unbiased estimate, is your summation x minus x bar square divided by n minus 1. So we are using n minus 1. So to get the unbiased estimate, we are using n minus 1 in the denominator. See here, this is the same. So this n minus 1 divided by n is kind of adjustment on the population variance, which is this. on the population variance to get the expected value of the estimated variance, right? Now how it is derived, so that can be explained. So it is simple. Expected value of like variance you can calculate it as sigma square minus sigma square divided by n, and then again there is a theory why we are doing this particular calculation. And if you solve this equation, that is sigma square minus sigma square divided by n, you will get this value, right? So I'll just give you the oral explanation, quick explanation. So you know this is variance estimate, okay? Variance of estimate, as in, you remember like in standard deviation we discussed about sigma square divided by n is like a standard error. So this is the standard error. This is your variance of population. So if you reduce standard error from the variance of population, you should get your expected value of sigma square estimate, right? That is a variance estimate. So this is the same explanation. Again, I'll just repeat this particular part, that is sigma square is your population variance, and we know that sigma square divided by n is the standard error in the population in the variance of your estimate. So this is the variance of estimate, okay? Variance of estimate, not the estimated variance. This is your estimated variance. Variance of estimate, as in whatever is your estimate, that is mean, in that estimate what is your variance. This is different and estimated variance is different. That's why I said like this is confusing, okay? So always think about it is in a different manner. This particular sigma square estimate is representative, maybe biased, unbiased, depending on the formula you are using, is the representative of the population variance, okay? So this particular part is the representative or the estimator of your population. Variance estimate is not the estimator of the population, it is the variance calculation of your estimated mean. So when you get your mean estimate, so what is the variance of mean estimate is calculated by using sigma square divided by n. This value will be very low if you have the sufficiently large number in large sample size, but this is not the case with the your variance estimate, estimated variance. This is even like confusing in speaking because variance estimate and estimate of variance and like that. So in case I'm mistakenly like reverse the words even in like coming session, so just remember what is the meaning, what we are trying to do here. So if you understand this logically, automatically you will be able to absorb the concept, right? So you got the formula here. Again I will repeat this. We know your sigma expected value of sigma square is equal to sigma square, or we can do it in a better manner, okay? So you know sigma square is equal to whatever is your expected value of your variance estimate, that is variance of population, is equal to expected value of variance, and then there is a bias which we need to add, which is sigma square divided by n. This is your bias, right? Here we are just shifting this term here and the formula becomes sigma estimated square, estimated variance, expected value of the estimated variance is equal to sigma square minus expected value of, not expected value of, minus sigma square divided by n, which is the standard error of estimated mean, like this. But we call it as a variance of estimate. We call this particular term as a variance of estimate. Simple. And then we will solve this equation. If you solve this equation, you will get result is n minus 1. This is a 5th standard mathematics. You should know how to do this calculation multiplied by sigma square. Okay. I hope you got the idea, like what is the calculation here. If you are able to understand this particular part, next part is very easy. That is a bias calculation. So bias calculation is same, formula is same. That is estimated variance, bias of the estimated variance is equal to expected value of square minus sigma square. Expected value of sigma square estimate and minus sigma square. If you solve this, you will get the answer. Answer is sigma square divided by, just a second, you have some correction here. Yeah, this is estimated value. Okay, then you know the formula for the expected value of estimated variance, and the formula is n minus 1 divided by n into sigma square minus sigma square, okay, is equal to formula is sigma square divided by n. This is your formula for bias of variance. So if you get the question on identify or calculate the bias of variance or estimated variance, you should use this formula. This is the point you are supposed to remember. Okay, and then you have like formula for variance square, sample variance is, that is s square. So sample variance formula is very simple, which is the same formula, summation xi minus mu square divided by n minus 1. In exam, you don't have to worry about this particular formula. You have to simply go with the your calculation, calculator calculation, like this. Okay, so this is clear, this is clear. Now you know like what is the bias and why we need to calculate the bias. You have to connect this particular part with the sampling distribution section, which we discussed in the first part of this series. If you are able to get it, then fine. Then we have the best linear unbiased estimator. Okay, so first is this term, best linear unbiased estimator. I'll just note down the first part. This is the unbiased. Unbiased in technical terms, which you are supposed to remember for the exam. In general, we already know that this expected value should be equal to your population value. But in proper terms, this is how you say it. Unbiased means expected value of estimate is equal to parameter you are trying to estimate. Okay, so mean is your blue is this particular term known as best linear unbiased estimator. So first term you are able to understand, like what is the unbiased, why this term is given for the unbiased estimator. Okay, so mean is your blue, unbiased estimator. So one first term is clear, unbiased. Estimator you already know, because mu estimate is estimator, so that's why estimator. And then best linear, what is the meaning of best linear? So there are different methodologies to estimate the population mean. Okay, so out of those different methods, we go with the calculation of your estimated mean. The methodology which we use for the calculation of mean is the linear method, and there are multiple linear methods, out of which the method which we are using currently, that is calculating the expected value using first building a taking the samples and then building the constructing the means, calculating the means, and then calculating the average of the averages, which we saw in the illustration of student score where we are taking this 20 samples scores, right? So this particular methodology is best linear because it is linear methodology, one, and it will give you the best results. So this particular estimate of mean should be close, very close to your population mean. Okay, so that's why we call it as a best and linear. So does this mean that this is the best methodology to calculate or estimate the mean, population mean? No, there are non-linear methods not discussed in your syllabus, so I will not mention any name. So again, the methodologies are a bit complicated, but mentioning name will not change anything. But there are non-linear methodologies, and these non-linear methodologies are able to produce better results or better estimate your population mean compared to this linear best. Okay, but we don't prefer non-linear methods, or this is what GAP says. So we generally don't prefer, because it includes the complications as in the calculation complications, and then you have to look for the goal, like are you looking for the accuracy or are you looking for the speed. Based on this, the linear non-linear method is decided generally. Okay, so here your focus should be on, you need to understand why we call it as a best linear unbiased estimator. Best linear because in linear format estimators this is the best. Okay, then second, unbiased because it gives the expected value of the estimate is equal to parameter you are trying to estimate. Okay, so we are saying the expected value of the estimate and not the actual estimated value, not just a samples average. It is the expected value of the estimate. That's why unbiased, and it is estimator. That's why it is estimator. And in combined format, this is known as the blue. So estimator is blue, means estimator is best linear unbiased estimator, like this. Very simple. I hope you got the idea. And one more thing, don't try to understand every part of it all at once. Just think everything in sections. So first we discussed about the population and sample movements. So think from that perspective. When we discuss the biased and unbiased estimator, what are the biased and unbiased, limit, think in that perspective. Then we discussed about calculation of the bias, think in that perspective. So don't try to intermingle everything, it will create a confusion, and then it will not fulfill our purpose for the exam. Okay, and we have similar discussions. Okay, so similar discussions as in even after this we have the discussions like this. So then we have the law of large numbers, CLT, which is the central limit theorem, and again we have all these processes, so where you are supposed to understand that particular part in that particular context and then move on. So we will see law of large number, then we will see CLT. Don't try to compare or don't try to directly understand law of large number and central limit theorem with the help of each other, because both are in a similar line but there is a difference. Okay, So it is better for you if you can differentiate between all these terms or the concepts. It will help you in scoring better in the exam. Then sample mean is, yeah, of course we know. Now law of large numbers and CLT, central limit theorem. This is known as CLT. This is known as LLN, law of large numbers. You have to clearly understand the difference between the two. You have to clearly remember that this is law of large numbers. Say, I will write down some statements. So you have to remember that this is law of large numbers and not the central limit theorem. And second statement is, say, this is central limit theorem and not the law of large numbers. So from that differentiating perspective, you have to remember these terms, right? So here we saw your sampling distribution, right? In sampling distribution, we selected some samples. Based on this, we calculate our mean, which is the estimate. And here we get our variance, that is how your sample estimate deviates from the population variance. And this variance is calculated using the sigma square divided by n, which is the variance of the estimate. I will repeat it again and again. This is the variance of estimate, not estimated variance. This is variance of estimate and not estimated variance. Okay, so this is your variance, right? And n is your data set n, that is total number of samples in your data set. Okay. To understand or to begin this, we have to first understand, that is to discuss the law of large number, we have to first understand what is the consistent estimator. So the term consistent estimator is, in general, if you ask me, so it is like as you increase the number of samples in your sample set, it should improve the accuracy of the estimator. Okay, so if this is happening, then we will call it as a consistent estimator. If the reverse is true, or even if you say you are increasing the sample, you are increasing the n, and your estimator is not improving, then we will call it as a estimator is not consistent. Okay, so consistent estimator is if you increase the sample size, then it should improve the accuracy. Now you have to remember it in the technical terms, like how you specifically or exactly say. Okay, I give you the general idea, understanding. It is good to understand, okay, but you need to remember line by line. But don't mug up, but remember the key terms. As the number of sample increases, sample parameter approaches to population parameter and bias reaches to 0 or reduces to 0. Better word is reduces. Right? So we discussed the similar concept, like what is a consistent estimator, and we are just saying like the accuracy of the estimator increases. Now same thing, same statement is written in this format. So there is no word accuracy used here. That's why I give you specific statement like what you are supposed to remember, because if the question comes in the exam based on this, so GAF will try to use these type of statement instead of improves accuracy. But improves accuracy is easy to understand. So consistent estimator means that as the number of sample increases, it improves, its accuracy increases. So it is so easy to understand, but for exam purpose, you have to remember this. So how, I will just read it out. As the number of sample increases, sample parameter approaches to population parameter, that is accuracy improves, and bias reduces to 0, again the accuracy improves, same thing. Then second hash 1 or 1 hash, whatever you like, as sample size increases, the variance of estimator approaches 0. Why so? Formula sigma square divided by n. If you increase it, say use 1000 and your variance is 20 and you are dividing it by 1000, so what is the result? It should be like very small, I guess 0.020, 10 cut, okay, yeah, approximately, okay, so maybe 10 here and there, but your answer will be 0. Now just take n is equal to 10 and your answer with this is 20 divided by 10 is 2. So if you increase the sample size, that is the n, this is n, if you increase the sample size, the variance of estimator approaches to 0, like this. Now what is the law of large numbers? Law of large numbers. Straight statement for law of large number is, and again here you must remember this in the statements, don't try to remember it in the concept, as in the conceptual clarity part should not be connected, or it should not be mixed with the law of large number, because the conceptual clarity for the LLN and the CLT looks similar. Okay, it might result into confusion, so remember it in the differentiating manner. So in LLN it says when LLN applies to estimate, this is the law, means estimator is consistent. And what is the law of large numbers? It is simple, increasing sample size results in better estimate. Okay, now see, first, when the LLN applies, if the LLN applies to estimate, okay, means estimator is consistent. Simple, this is how you should remember. Again we are discussing the same thing, that is if you increase the sample size, then it will automatically improve the accuracy of your estimate, right? But here in the law terms, in the this particular law of large number terms, you have to remember like this, like when the LLN applies to estimate, means the estimator is consistent. And what is the consistent? Consistent means as the sample size increases, it will improve the accuracy. And again, for improve the accuracy, we have that technical term like population sample parameter will approach to population parameter, like this, right? So it is kind of getting intermingled everywhere, right? So that's why remember it separately. Then increasing the sample size results in the better estimate is your law of large numbers. Then center limit theorem, CLT. This states, and it relates to sampling distribution, that is CLT is for the sampling distribution. I guess it is not mentioned in your book, don't know why. Only applies to sampling distribution. Okay, so it states that the sampling distribution of sample mean mu approaches to normal distribution as That is normal probability distribution. In like here in book, the language is normal probability distribution. I'm just writing the normal distribution because you know normal distribution is a normal probability distribution to normal distribution with mean mu. Okay, now understand this. Very critical, highly testable, both. Say this is your population. This is how the population is distributed. Okay, we have different sample values. Now we will take sample, say sample size of 50. Okay, so n is equal to 50 here, which is sufficiently large sample. You have to remember this sufficiently large sample. I will tell you what is a sufficiently large sample for the CLT, but for now just remember this. If you take this particular sample of 50, okay, and you keep doing it, we know the process, right? So select 50 samples, calculate the average, reserve the average, calculate the average, reserve the average, call it as mu1. Now we will use 1 2 3. Then for second sample mu2, for third sample mu3, for fourth sample mu4, and so on till you get the mu-n last sample. Okay, samples mean, and then we will calculate the distribution or build the distribution using all these means, right? So if you do this, see what will happen. If your sample size is large enough, what is the large enough? That is n is equal to or greater than 30. So 30, 31, anything is fine for us. If you use the sample size which is large enough, then the sampling distribution will have mean mu, which is exactly the mean of population. So this mean and this mean is same, right? And so this is your first condition, sorry. Okay, and this distribution of this population's mean, so population is this. If you build a sampling distribution of this population's sample sets, then you will get a normal distribution. Okay, so no matter how the distribution is for the population, if you build the sampling distribution, two things will happen. First thing is your mean will be equal to, that is population, the sampling distribution's mean will be equal to the mean of the population. One, this is the CLT says, central limit theorem says. And second thing which will happen is that your this distribution of sampling distribution will be normal and irrespective of how the population distribution is. So both are different. No matter what distribution is, like this or whatever is the shape of the population distribution, you will always get the same sampling distribution, that is a normally distributed sampling distribution. But what is the condition? Condition is your sample should be large enough, like this. So this is your CLT, central limit theorem. And one more property, this property you already know. Variance of this estimate is equal to sigma square divided by n. right? So if you increase n, automatically your standard error will reduce, right? Variance will reduce, meaning you are approaching the accuracy. So your analysis is accurate. We can say this, right? Now assumptions. These are the important assumptions. Assumptions in LLN, law of large numbers, and CLT. There is no explanation of why these assumptions are there, but you have to remember this: LLN and CLT. For LLN, mean is finite. Okay, why so? Because see, this LLN only discusses or deals with the mean, right? So if you increase the sample size, then your mean will be accurate like this. So that's why it is only concerned with the means infiniteness. If the mean is infinite, then practically you cannot execute the calculation, right? So that's why mean is finite is the assumption of LLN. Remember this. Same assumption is applicable here in CLT, that mean is finite, but because you are also discussing or using or calculating the variance of the estimate using population variance, here variance should also be, variance is also finite. So here you need two assumptions in this LLN. You need only one assumption, and then there is third assumption here, added assumption. Third is it does not require, which we already discussed, does not require assumption of normal distribution of population. Okay, I hope you are getting it. Why? Because see, we discussed, right, that is, no matter what is the size or the shape of the population distribution, your sampling distribution will always be normal distribution, right? So we don't need to assume that your population distribution is normal. Irrespective of whatever it is, we know that our result will be normal distribution. Okay, I hope you got the idea. This is really critical, like what to remember, what not to remember, and like that. So please make sure you remember this. And because we know that CLT allows us to build a normal distribution using the of the population, we get the facility to use mean in our calculation for building the confidence interval in hypothesis testing. Okay, so CLT is the thing, because this we have already discussed in the hypothesis testing chapter. So CLT is that rule which allows us to use any population in hypothesis testing, because the ultimate result, this is normal distribution, and we can get the values from your student tree distribution or normal distribution z values like this. If you want to use the z values, you must have the normal distribution. If you don't have the normal distribution, then you cannot use it. So I got the mean here using this particular calculation, and I will get the variance. Simple. So that's why you can use it in the hypothesis testing. So you have to always remember this. The CLT is the reason why we are allowed to use mean and the standard variance of the standard error in your hypothesis testing calculation to build the confidence interval. Now properties of CLT. You have to remember it as it is. You already know all the properties. I'm just writing down the statements. So 1, if the sample size is sufficiently large, sampling distribution is normally distributed. Is the mean of the population, I'm just writing down the pop to reduce the writing time, which is mean, and the mean of distribution of all possible outcomes of sample mean are equal. You know now what is a distribution, right? So are equal. But the way it is written in the book is the mean of the population mu and the mean of the distribution of all the possible sample means are equal. So at the end we know how we build the sampling distribution. We can call it as a sampling distribution, right? Sampling distribution is distribution of mean of all the possible outcomes based on the n. N is important here. And then the variance of the distribution remember, I am adding my statement, not population. Always remember this, not population, not population. Okay, variance of distribution of sample mean is sigma square divided by n, that is your standard error, and this approaches to 0 as the sample size increases. This approaches to 0 as sample size increases, right? So this is the end of your CLT, law of large numbers and all. Then we have the skewness kurtosis discussion. This is exactly same discussion, so I will give you the quick overview of skewness kurtosis in the third part. Skewness kurtosis, mean, median, mode, quartiles, quantiles, IQRs, interquartile range and everything. So everything is discussed here, and we need to, because we already know it, where we will discuss it in a like revision style manner. And then you have the co-skewness and co-kurtosis, highly non-testable area. So that part we will discuss in the third part. So we'll close in the third part. Now take a break. Thank you.